So today we are going to be looking at Ethernet switching. Our objectives for this class are: one, we're going to be looking at what an Ethernet frame is. We'll be explaining how the Ethernet sublayers are related to the frame fields. We'll be discussing the Ethernet media access control address. We are going to be looking at the MAC address table. Here we're going to be looking at how a switch builds its MAC address table and forwards the frames. We'll also be looking at switch speeds, forwarding methods, and in this we're looking at the description of how the switch forwards frames, the port settings, and basically a general overview of how a switch does the roles that it plays. So as discussed earlier, the networking functions are broken down and explained or illustrated in form of layers. All the functions of a network are described in form of layers. So each layer has a specific function and a number of protocols that are going to be running on that layer, performing a specific function. So all those layers combined have the protocols that enable networking to actually occur. So if we can have a small recap. So here I have a small animation that explains to us how networking actually occurs. So we have PC1 and PC number 2. So if those two are to communicate, data is sent from one PC to another. Data is passed down the layers of the OSI reference model, which we are going to be illustrating shortly. At the very top, we have what they call the application layer, transport, network, and the link layer. As data moves from the application layer to the transport layer, the data information is added, it becomes a segment. At the network layer, information is added, it becomes a packet. At the link layer, additional information is added and it becomes a frame. That process is called encapsulation. Now that frame is passed down to the physical layer and is encoded into bits that are transmitted to the destination. And the destination, it is decoded back into the original message. The bits make the frame makes the packet goes back to the segment, and the segment is stripped and makes the actual data. So in brief, that's how networking actually occurs. So as explained earlier, Ethernet operates at the data link as well as the physical layer. Ethernet is the protocol that the Ethernet operates at the data link and the physical layer. It is in the family of networking technologies identified and defined in the IEEE 802.2 and 802.3 standards. So the link layer is comprised of two sublayers. One is called the link logical control sublayer and the media access control sublayers. So the function of the link layer are divided between two sublayers, each performing a specific function, but both their functions combined make up the entire functions of the link layer. So at those two layers, the data link and the physical, we have Ethernet as a protocol that is running there. The 802 local area network and metropolitan area standards, including Ethernet, will make use of the two sublayers. We talked about the link logical control sublayer. This one is responsible for placing information to identify which network layer protocol is being used in the frame. So since this is the sublayer that's closest to the network layer, it's responsible for the communication with the network layer. So it will include the information it has learned from the network layer. Then we also have the media access control layer. Now this one is closest to the physical layer. This one is responsible for the process called encapsulation. It will then is responsible for getting the frame, the packet, and packaging it into what they call a frame, which we saw there in the earlier animations. So it's also responsible for the media access control. Media access control is a process by which devices are able to transmit their data on a shared medium. Yeah, it's called media access control. It determines when devices can begin transmitting. So it's also responsible for providing what they call data link layer addressing. So in addition to the addressing that has been learned from the network layer, that is the IP addresses, additional addressing is provided for by the media access control layer. And that addressing is called the MAC address, or the media access control address, or sometimes called the physical address. So the media access control sublayer is responsible for what they call data encapsulation, as well as accessing the media. As I explained earlier, encapsulation is the process of packaging, which we saw in the animation. At every layer, data is encapsulated and becomes a different data type, becomes a packet, becomes a frame. So what is encapsulation involved with? The IEEE 802 data encapsulation includes the following. It defines the internal structure of a frame. It is responsible for adding addressing. The Ethernet frame includes both the source and destination media access control address, and this is what is used to deliver a frame from one network interface card on the same network to another interface card on the same network. So when your PCs are exchanging data among themselves within the same network, they use the media access control addresses. However, when they are communicating across different networks, they use the IP addresses because those ones help identify the source and destination networks. However, on the same network, they will use the source and destination media access control address. Then also, the media access control layer is responsible for Ethernet error detection. Now, before two devices transmit data, they will calculate something called a checksum. That checksum is then stored in a field called the frame check sequence trailer. When a sender is sending data, they calculate what they call a checksum and store it in the frame check sequence trailer. When that frame has been received by destination, the destination will also calculate a checksum and then compare against the value it has got against the value in the frame check sequence trailer. There, it will be able to know if the data has been corrupted or has any errors because it compares its value with the value that was sent, whether that was created by the sender, and that value is saved in the frame check sequence trailer field. So another function about another function done by the media access control layer, as explained earlier, is media access. The IEEE 802.3 media access sublayer includes the specification for different Ethernet communication standards over various types of media, for example, copper or fiber. So as we know, this layer is responsible for accessing media, but the medias can be different. We can have fiber, we can have wireless, we can have copper. So the media access control sublayer will define what access method to use when accessing fiber, what access method should be used when accessing wireless, what media access method should be used when using copper cable. So it defines the various standards. So the old Ethernet networks, that is the legacy Ethernet networks, they were using topologies like the bus. We know what a bus is. It's a wire with all the computers connected to it. They were using bus topologies and hubs. Now with hubs and bus topologies, devices only communicate in half duplex. With half duplex, it means that only one device can send or receive at a time on the entire media. Meaning that much as you have a hub with 10 computers, only one computer can communicate at a time. If you have a bus topology, 60 computers, only one device can transmit at a time. Now, what happens here is that because they're operating at they're all operating at half duplex, that is, one can only transmit at a time. It means that all of them are going to be competing for the media, meaning that all of them need to transmit, but only one can transmit at a time, which means they compete for the media. For that case, it led to situations whereby two devices would transmit at the same time in a half duplex environment, which would lead to collisions. And there had to be a way in which access is going to be managed. So that led to the development of contention-based access methods. Contention-based access methods were methods that were created to enable devices that are operating in a half duplex environment to be able to transmit data because the media was for contention. Only one could transmit at a time, so they all competed for it. An example of a contention method was the carrier sense multiple access with collision detection. Now, this was a contention-based method that enabled devices to keep transmitting because it took into account the fact that two devices may be able to transmit at the same time. And once they transmit at the same time, there was likelihood that their data would collide, that is, their frames would collide because only one device can transmit at a time. So this led to an access method called the carrier sense multiple access with collision detection, because with this one, it enabled situations like where there was a collision to be detected, and when detected, devices were supposed to act in a specific way to prevent against further collisions. However, in today's networks, we don't require the carrier sense multiple access with communication because we're using switches, not hubs. And switches are full duplex. They don't work in half duplex. This has removed the need for using the access method called the carrier sense multiple access with collision detection because there are no more collisions. Now, one of the properties of Ethernet is that it defines the frame fields. Now, a frame, as we explained, is a data type that's created running layer, and a frame has a number of requirements. First thing is a frame has to have a minimum and maximum size. The minimum size of a frame is 64 bytes, and the maximum is 1518 bytes. Any frame less than 16 bytes is considered a collision fragment. A collision fragment is a frame that has been created as a result of two frames colliding together, especially in a half-duplex environment. When two frames collide, the frame breaks into bits and pieces which are less than 64 bytes, and those bits and pieces are called runs or collision fragments. Then we also have frames that are larger than 1500 bytes. These are considered jumbo or baby giants. If the size of a transmitted frame is less than the minimum or greater than the maximum, the receiving device normally by default drops the frame. Dropped frames are likely as a result of collisions or other unwanted signals. However, these are normally considered invalid because they don't meet the size requirements and are always dropped. However, because of the advancements in the technology, we have now faster switches. Previously, in the Ethernet switches which are running at 10 Mbps, baby giants will be dropped. However, now baby giants are acceptable because the switches are faster. We have fast Ethernet switches running at 100 gigabits per second and gigabit switches running at 1,000,000 bits per second. So what will happen here is that because the switches are much faster, support higher speeds, they're able to take larger frames. So baby giants, will find that they'll be common in fast Ethernet switches and gigabit ones because they are more faster switches. They run at 100 Mbps and 1,000 Mbps. So ideally, in the older switches, that is the Ethernet switches running at 10 Mbps, you'll find that they would be dropping jumbo frames. However, the faster switches now accept the frames. So when you look at the size of a frame field, we don't look at the preamble or the start of the frame. We only consider the other fields. The source and destination addresses normally take up about 12 bytes. The type length takes about 2 bytes. The data takes between 45 and 1500 bytes, and the frame check sequence takes 4 bytes. So each of those fields has to have that as the size it occupies. Data field is the one that is variable because this one will contain data of various sizes. So it's between 45 and 1500, but the other fields are all fixed in size. So here, I am going to open up my Wireshark to show you how to analyze these frames, and I'll be showing you the various parts of a frame. So here I have my Wireshark. Within my Wireshark, I can see my active interfaces, my Wi-Fi. Let me see if I can make this a bit bigger. I'll zoom a little bit. Oh, sorry, I don't have zoom. So let me just quickly open this up. Here I have my frames that have been traversing. So as you see here, this is all active on my system. So this is all traffic. I can simply stop it, and then I click on any one of them. And when I click on one of them, it will open up at the bottom here, and I'll be able to see the parts of the frame. So I see the word frame here. This is the frame. It's an Ethernet type of frame. I can see in this Ethernet frame, I see the source, the destination address, you see over here. And then here also, I see the source address. This is the source and destination. So remember, within the frame, we find the packet. This is a section of the packet here. We have the source IP address and destination IP address, as well as the version. So these are the various parts of the frame. And here we have the data. Remember, when you're transmitting data between systems, a single bit of data is broken into bits and pieces. Yeah, they are sequenced and sent, and as the recipient, they are built back into the original message. So here, as you see, we have the checksum here for error checking. We have the actual data here on the right side. This is a frame. source, destination, source, destination. This is the packet info. This is the frame info. And that's that. So we continue. So that's Wireshark. So when you get time, please download Wireshark, install it, and use it to analyze the traffic that's happening on your network. So what's an Ethernet MAC address? An Ethernet MAC address consists of a 48-bit binary value expressed in the form of 12 hexadecimal values. Given that 8 bits makes a byte, it's a common binary grouping that binary, that is 8 zeros, and 8 ones is represented by 00FF. When using hexadecimal, leading zeros are always displayed to complete the 8-bit representation. For example, the binary value 000 and 000 and 1010 can be represented in hexadecimal as OA. Hexadecimal numbers are often represented by a value preceding OX to distinguish between decimal and hexadecimal values in documentation. Hexadecimal may also be represented by a subscript of 16 or a hex followed by an H. So generally, MAC addresses are always represented in hexadecimal because with hexadecimal, we can have a 48-bit binary value. So we don't use decimal because hexadecimal supports for more values. And normally within these MAC addresses, because of the need for uniqueness, we always use hexadecimal. So in an Ethernet local area network, every network device is connected to the same shared media. The MAC addressing provides a method for device identification at the link layer of the OSI model. An Ethernet MAC address is a 48-bit address represented in 12 hexadecimal digits because a byte equals 1 byte is equal to 8 bits. We can also say a MAC address is also 6 bytes in length. All MAC addresses must be unique to an Ethernet device or Ethernet interface, and to ensure this, all vendors that sell devices must register with IEEE to obtain a unique 6-bit hexadecimal code called an organizationally unique identifier. Let me explain this better. Whenever manufacturers of these devices, these computing devices we use that require to access a network, are going to make or manufacture a network card, they have to go to IEEE and register themselves as a manufacturer. And when they go to IEEE to register themselves as a manufacturer, IEEE will give them something called an organizationally unique identifier. So Dell has its own OIU, HP has its own OIU, Acer, Huawei, Techno, all those companies. For as long as you have a device that needs to access the internet, it will be given an OIU. So this OIU identifies the vendor or the manufacturer of a specific network card. So when you guys go into cybersecurity, these are some of the things that you'll be looking at. You're able to know the manufacturer or the brand of a device by simply looking at its MAC address. Every device has a unique MAC address because one part of it identifies who manufactured it, and then the other part is vendor assigned. Now, the vendor assigned is the identity of that card within the manufacturer's cards. For example, you will have 3 laptops from Dell. All of them will have the same OIU because they are all Dell machines, but all of them will have a different vendor assigned number to distinguish one laptop from another within the HP laptops. So let me show you how that looks like. First of all, how do you find out the MAC address of your computer? The MAC address of your computer can simply be got from your command prompt. So on your command prompt, you simply issue the command IP config /or. So what you see here, what's called a physical address is actually your MAC address. So if you're using Wi-Fi, you'll have a MAC address. If you're using cable, which is Ethernet, you will also have another MAC address. So each card, even if you have the same laptop, but wireless and wired card, you have 2 different MAC addresses. So every network device or network interface card already has a MAC address. So that's the identifier of a device on a network. It's built in by the manufacturer because part of it identifies the manufacturer and the other one identifies the actual device on the network. So if I go back to my Wireshark, I'll show you a few samples. So Wireshark is able to get you the OIU. So let me look for any device here. See if I can find any other device. Let me go back to capture and start. So here, I'll let's say look for any type of data here. So for example, here, if you look at my output here, you see that my first part, this is my MAC address for the source. But you see here, it is showing me the owner of the OIU, Huawei Techno, which is my phone, okay? And notice that the first part of the MAC address, which I explained earlier, is the OIU. It is this part over here. And then the last part is vendor assigned. So if you look back here and compare these MAC addresses, from 9B is vendor assigned. This 14A, A51A is the OIU for Huawei, okay? And then if I look at another one, there's another one here. There's another one here for Cisco Linksys. You see here, Cisco Linksys. This is the OIU. So 0768 is part here, 07. This is the vendor assigned here. Okay. So let me change a bit. So remove all this. So now here can pick any other. Let me see here. So you see here this is Cisco Linksys and Intel. So these are the OIUs, the first part of the MAC address. So this first part up to D8 here. This is the vendor assigned, this is the OIU. Cisco helps translate the OIUs into the actual names. Does a search for you. So go on. So when a device is forwarding a message to an Ethernet network, the Ethernet header will include the source and destination MAC address, which I just showed you previously in Packet Trace in the Wireshark. When a network interface card receives an Ethernet frame, it examines the destination MAC address to see if it matches the physical address that is stored in RAM. So what will happen here is that before a device can transmit data, before a device can process any data, it receives any frame, it first compares the MAC address in the destination to see if it matches with its own. If it matches, it passes it up the layers for processing. If it doesn't, it simply drops the frame. So any device that is a source or destination of an Ethernet frame will have a network interface card, and therefore a MAC address. So any device communicating with a network has to have a network interface card, because a network interface card enables them to connect to a network. And for that reason, because they have a card, they need to have a MAC address. So in Ethernet, different MAC addresses are used for layer 2. We have unicast, which is a one-to-one communication, broadcast, which is a one-to-all, and then multicast, which is a one-to-many. A unicast MAC address is normally a unique address that is used to send from a single transmitting device to a single destination device. The process that a host uses to determine the MAC address with the associated IP version 4 address is called the address resolution protocol. The process that a source host uses to determine the destination MAC address associated with an IP version 6 address is known as neighbor discovery. The source MAC address must always be unicast. So let me show you a unicast MAC address. So here is an example of a unicast MAC address. A unicast MAC address is a situation normally where you have a one system communicating with another one system. For example, you see this is one different system with another different system. So what you see here is a unicast MAC address. One MAC address different from the other. That's what they call a unicast address. Here it is one source MAC address, you see here, so one destination MAC address and a different source address. So two different MAC addresses of communicating device. This is a unicast MAC address. So continue. Then now what they call a broadcast MAC address. So in Ethernet broadcast, an Ethernet broadcast frame is normally received and processed by every device of the Ethernet LAN. The features of an Ethernet broadcast are as follows. If a device, if the destination has, it normally has a destination MAC address of FFFF in hexadecimal, and when this frame is received, it is flooded out on all the ports except the incoming port and is not forwarded by the router. If the encapsulated data is an IP version 4 broadcast packet, it means that it contains all ones. So the MAC address will have all Fs. So let's look into our Wireshark and see if we can find a sample broadcast. So I'll use the ribbon up here and I'll choose broadcast, Ethernet broadcast. So let's wait and see if we can find any broadcast. So here we have our broadcast packets. So if you see here in the frame, broadcast destination is FFF. So this is what they call a broadcast. So you go back. So that's what they call a broadcast. Remember what they call a multicast? A multicast is an Ethernet frame being received and processed by a group of devices that belong to the same multicast group. So in this case, there will be a destination MAC address for IP version 4 of 01005E. And this will be normally a multicast packet. And you will have a destination MAC of 33-33 when encapsulated data is an IP version 6 packet. There are other reserved multicast destination MAC addresses for the encapsulated data when it's not IP, such as a spanning tree. It is normally flooded out on all the ports of the Ethernet except the incoming port, unless the switch has been configured for multicast snooping. Simply because multicast addresses represent a group of addresses, they can only be used as a destination of a packet. A source will always be a unicast address. As with the unicast and broadcasting addresses, multicast IPs require corresponding multicast MAC addresses. So I'll try to see if we can find a multicast, either IP version 4 or IP version 6. So let's try here and try with IP version 6. Let's see. So we don't seem to have any multicast traffic here because we're in a LAN that's not IP version 6. But this one I think I'll show it to you in the labs. When we see IP version 6, please open up the packet so that you can view the multicast traffic. So we continue. So I am going to set up a small topology, and then we'll look at how to view the MAC addresses, how you configure devices and verify connectivity, and so on and so forth. Now, a layer 2 switch is a device that interconnects devices together, and it will use a media access control address or MAC address to make the forwarding decisions. Normally, the switch will be completely unaware of the data protocol being used in the data portion of the frame, such as the IP version 4 packet, an RRP, or an IP version 6 neighbor discovery packet. Ethernet switches examine the MAC address table to make forwarding decisions for each frame, unlike legacy Ethernet hubs that repeat out on all the ports apart from the incoming port. When a switch is turned on, the MAC address table is normally empty. So I'm going to demonstrate this to you so that we can quickly go through it and understand what this is about. So let me quickly open up my packet tracer. So here I have my packet tracer. So let me quickly add a 2960 switch So I put the devices down here, 960, I add it there. So what I plan to do is add about 3 PCs. 1, 2, 3, 4. Then I interconnect them. So then we are going to give these PCs IP addresses. Okay, so we're going to give them IP addresses that are actually on the same network. We're going to give them IP addresses on the same network. So the IP addresses I've chosen, are 192. So let me begin with PC number 1, PC number 0, sorry. Let me begin with PC number 0. So I'll begin with PC number 0. So open up PC 0. So we all know how to assign IP addresses to the PCs. We all know how to assign addresses to the PCs. So let me assign my PC an IP address. Just a second. Just a second. Just a second. Just a second. Press a PC 0. Okay. So I begin with PC number 0. I assigned an IP address 192.168.2.1. Get to PC number 1. Just a minute. First close this a minute. Let me first PC 0. This PC 0. See here. Just 1 minute. PC 0. I can't seem to get PC 0. Okay, just a minute. PC 0. Okay. Okay, so let me quickly assign these PCs addresses real quick. PC 0, 192.168.2.1. PC 1, 192.168. .2.2. And the next one, 192.168.2.3. And 192.168.2.4. So these are the IPs that given the PCs 192.168.2.4. Now to show you the MAC address table, I simply open up the switch. Hopefully you can see the switch. Now in the switch, I run the command show, say enable, show MAC address table. So as you see here, every PC and its MAC address are going to be associated with a port that they're connected to. So how this works is that the switch does what they call the learning. It will learn the MAC address of the PC connected to that port, and then associate the MAC address of that PC, that respective port. Okay. So if I go back here, PC 0. Let's see if I can get PC. So that's pretty much how a switch does it. So you can begin by pinging one PC from the other PC, and you should be able to see the MAC address table. So the MAC address table, you run the command show MAC address table. It will show you the MAC address of that respective PC. So you can ping the two. Second. So that's that. So let's quickly go back to the chapter. So how does this work? I can explain what we've just observed. So one of the states a switch goes through is learning and forwarding. So what will happen here is that the moment you connect a device and begins communicating on the switch, the first thing a switch will do is go into something called examining. Now, every frame that enters a switch is checked for new information to learn, and this is done by examining the source MAC address of the frame and the port number where the frame entered the switch. If the source MAC address does not exist, it's added to the table along with the incoming port number. If the source MAC address does not exist, the switch updates the refresh timer for that entry by default for every 5 minutes. So what will happen here is that when the PCs are connected to the ports on which we connected them, the switch will learn the MAC address of that PC and the port at which it is located. Now, when a switch is sending a frame to another destination system, it still looks at the MAC address table to know where to send it to. So what will happen here is that a frame will go to the switch will then look at the destination of that frame and then compare the destination address with what it has in its MAC address table. Where it sees a match, it automatically forwards it to the frame. So if I go back to my packet tracer here, I go back to my packet tracer and I show the MAC address table, and I show you the MAC address table. So as you see here, if a frame is coming from a PC on port 4 and the switch sees the destination is ending with 183, it sends it automatically to port number 2. So a frame comes, a switch looks at the destination address, compares with what it has in its MAC address table, and then knows which port to forward it to. So the switch will create the MAC address table by learning who is connected on which port. After learning that, if a frame comes going to a specific destination, it then looks at the MAC address table it created to find out where is the MAC address on which port is this destination MAC address located, and then it will forward it out to the respective port. That's how the MAC address table works. So that's learning. Continue. Now, as the switch receives frames from different devices, it's able to populate the MAC address table, which I just showed you earlier, by examining the source MAC address of every frame. When the MAC address of a table, when the MAC address table of a switch contains destination MAC addresses, it is able to filter the frame and forward it out of a single port. So as we see here, we have ports with the MAC addresses of the devices associated with it. So to test this, please make sure you give your PC's IP addresses, have them ping each other, and then look at your MAC address tables. So within your notes, you'll see a video on how switches build the MAC address tables and how switches forward frames out of their MAC address tables. So in the same way, you look at a video telling you how a frame is sent to a default gateway and how a switch does that within your notes. So I won't copy ours. I do spend so much time with that. And here also we built a lab and we have configured a simple network, and we've seen how the communication actually occurs. Then we have forwarding methods. Now we have a number of forwarding methods found in Cisco switches, and these forwarding methods normally they determine how fast a switch moves data after it has discovered the destination from one port to another. We have two main methods. One is called store and forward switching, another is called cut-through switching. The store and forward switching, in this case, it's a frame forwarding method that receives the entire frame, completes the cyclic redundancy check. If the check is valid, it looks for the destination address and forwards it out to the correct port. We have cut-through switching. In this case, it's frame forwarding method whereby a frame is not looked at in entirety, but the basic minimum, it looks simply at the destination address and forwards it to the destination. So the big advantage of store and forward switching is that it determines if a frame has errors before propagating the frame. And when an error is detected, the switch will discard the frame, and discarding of frames with errors reduces the amount of bandwidth consumed by corrupt data. Store and forward switching is required for quality of service because in this case, it helps easily classify data and enables easier data prioritization. Quality of service is a situation whereby data has to be given different priority over other data when being transmitted. But it can only happen if the data has been stored fast, so it can be analyzed to be prioritized. So for that reason, store and forward is the only one where you'll find quality of service being implemented. Quality of service is common in implementations of voice over IP, whereby voice over IP traffic needs to be given traffic over other traffic like web browsing. So then we have cut-through switching. With cut-through switching, a switch acts upon the data as soon as it's received, even if the data is not complete. The switch buffers just enough of the frame to read the destination MAC address so that it can determine which port to forward the data out of. The switch doesn't perform any error checking of the frame. However, there are two variants of cut-through switching. Fast forward switching, this one offers the lowest delay, and in this case, it will quickly forward the frame the moment it receives it. It simply looks at the destination address and forwards it. Remember what they call fragment-free switching? The idea behind fragment-free is to at least check the first 64 bytes of the frame to ensure that it's not a collision frame and then transmit it. So it offers higher latency and higher integrity of store and forward by only checking to see if the data, the frame meets the minimum size. So it checks the first 64 bytes. If they're okay, it then forwards it to the destination. So the end goal here is to prevent against forwarding of collision frames. So in store and forward, of course, as explained earlier, the frame is first stored in a buffer, checked, and then transmitted. Now we have different types of memory buffers that are used in store and forward. We have port-based memory buffers and shared memory buffers. In port-based memory, frames are stored in queues that are linked to specific incoming and outgoing ports. In this case, every port has its own memory, and in that memory, we'll have queues. So a frame is transmitted to the outgoing port only when all the other frames ahead of the queue have been successfully transmitted. So switches are going to be receiving frames and put them in a queue, first come, first serve. And a frame is only processed after the frame before it has been worked on. So it is possible for a single frame to delay the entire transmission of the frames in memory because of the busy destination ports. This delay occurs even if other frames could be transmitted. This frame occurs even if other frames could be transmitted to open destination. So they are all in queues until they are processed. In shared memory, in this case, all frames are deposited into common memory buffer, which is shared by all the ports. And frames in the buffer are dynamically linked to destination ports, enabling packets to be received in one port and transmitted out of another port without moving to different queue. Shared memory buffering also results into larger frames being transmitted and fewer being dropped. And this is important when you're having things like asymmetric switching, which allows for different data rates on different ports. Therefore, more bandwidth can be dedicated to specific ports. So shared memory, you have memory being used by all the ports, the same memory being used by all the ports. With port-based memory, you have memory being allocated to specific ports. Of course, we discussed that as a disadvantage in that in those ports, in that port-based memory, you find queues associated with a specific port, which can lead to delays. So another factor of the switches is the duplex settings. Duplex settings are commonly two main duplex settings. We have what they call the half duplex, where both ends can receive and receive at the same time, and half duplex, where only one device can send or receive at a time. Now, within there, we have something called auto negotiation. Auto negotiation is commonly found in most switches and network interface cards because it enables two devices to automatically negotiate the best speed and duplex capabilities. Only gigabit Ethernet ports operate in full duplex by default. So then we have what they call a duplex mismatch. A duplex mismatch is one of the most common causes of performance issues on 10 and 100 Mbps Ethernet links. It normally occurs when one link operates in half duplex while the other port operates at full duplex. This can occur in one or more ports if one or more port links are reset, and auto negotiation does not result into the link partners having the same configuration. It can also occur when users configure one side of a link and forget to configure the other. Both sides of a link should have auto negotiation on, or both sides should have it off. The best practice is to configure Ethernet ports as switch ports as full duplex. We also have the auto MDIX. Auto MDIX is a connection between devices that was once required using a crossover. So as discussed previously, devices that are similar would use crossovers to link them together, and devices that were not similar would use a straight through. But now, because of the changes and advancements in technology, we have something called auto MDIX, the automatic medium, the automatic medium, the automatic medium, the auto MDIX, which stands for the automatic medium independent interface crossover. So with this, it enables you to use a crossover to link a PC to a PC, that is like devices, a router to a router, and so on and so forth. So in this case, the ports, network interface cards automatically configure themselves to detect the kind of cable you're using and enable the communication to continue without having to change the cable type. So let me quickly demonstrate to you how the duplex applies and the duplex settings happen. So I'll quickly go back to my packet tracer here and explain to you. Now, one of the common devices that work in half duplex is a hub. Okay? So I'll add a hub in my topology. So I'll first minimize on the switch. I'll add a hub in my topology. So you can get the hubs from network devices and hubs, and I'll get a PT hub, and this PT hub, I'll add a PC to it. I'll disconnect PC from here, and now I'll connect this PC to the hub, and then the hub to the switch. Hope that makes sense. So then I'll open up my PC. Number 3, I'll give it an IP address 192.168.2.4 as you've seen. Okay, my PC number 1, PC number 0, sorry. I can also open it up. PC number 0 with my PC number 0. Oh, I have PC number 0. Okay, fine. I'll use PC number 1. So I use my PC number 1. I'll open it up here. PC number 1, the IP is 192.168.2.2 as I explained earlier. PC number 2, I can also open it up. So PC number 2, the IP address is 192.168.2.3. Okay, so the first thing I need to check here is the PC should be able to communicate. So I'll set ping 192.168.2.2. I get replies. Another one, 2.3, I get replies. And then 2.4, I also get replies. So because the PCs are exchanging data, okay, I have to check my MAC address table on which everything was based. So I open up my switch. When I run the command show MAC address table, press enter, say enable show MAC address table. So it shows me all the ports on which those 3 PCs are located. Okay, so if PC on port 4 wants to communicate with the PC on port 2, all they do is the switch looks at the destination address. Where it says a match, it forwards to the port. Okay, so now let's look at the duplex settings. As you see here in our packet tracer, we have a connection with a hub. Okay, we have a connection with the hub. So if you look at the hub is connected on port number fast Ethernet 0/1. That is on the switch side. So let's look at the duplex settings of this port. So remember, it is a hub connecting with a switch. So let's look at the duplex settings of this port. So remember, it is fast Ethernet. Remember, it's fast Ethernet 0/1 on the switch. So to view those settings, I simply issue the command show interface fast Ethernet 0/1. So if you notice here, it is running in half duplex. It's running in half duplex because this port has something called auto negotiation. Auto negotiation enables the switch to detect the duplex settings of the switch, which is half duplex, and automatically adjust itself. So you see what happens when I change the duplex to full. Let's say configure terminal. And I say interface fast Ethernet 0/1, and I use a special command called duplex full. So the moment I set duplex full, immediately the interface goes down, because there's now what they call a duplex mismatch. Duplex mismatch is a situation whereby the 2 devices on both ends have different duplex settings. They don't have the same duplex settings. So you see what happens when I say duplex half. When I say duplex half, it means now the duplex settings on both sides will have matched, and both interfaces will now come back up. The other alternative to saying duplex half is by simply saying duplex auto. So I'll try by first saying duplex full so that it goes down because there's a duplex mismatch. And then now let me say duplex auto, which is auto negotiation. This one automatically detects the duplex settings of the other side, and the interface will automatically come up, and then eventually there will be communication. So that's all for today for this chapter. I hope these YouTube links work well and are able to explain to you and are able to guide you in your practicals as you work. And I'll be sharing these as we go on.